Hello, everybody. This is Veysel. I'm a PhD candidate at LIAX, and I'm also a principal data scientist at Johnson Labs, which is a healthcare AI company. We are developing Spark NLP over there. So at LIAX, I'm working with computer vision and NLP at the moment. So today, as a guest lecturer, I'm going to let you jump into neural networks because you are already learning machine learning, and the next step will be neural networks. So in this talk, in the next 1.5 hours, I'm trying to get you learn the basics of neural networks and what is the difference between neural networks and the machine learning and the deep learnings, and then cover some use cases, and finally I'm going to go one by one at each step how to train a neural network from scratch. Okay, this is not a hands-on session, but we'll try to get you warmed up in neural networks actually. So let's start. As you know, people use AI, machine learning, or deep learning terms interchangeably, so which is wrong actually, because there are some differences and there are some jokes about that actually, because the people try to sell the ideas by using some fancy terms like AI or deep learning, So let's start explaining each term one by one. So what is artificial intelligence? It is the higher level, actually. It's the roof term covering all machine learning and deep learning terminologies. So it is exactly like trying to build a system that could think like a human, reasoning like a human, and then accomplish the task as human can do. So it's not just machine learning or deep learning. So it's the roof term. So under that, there's a machine learning, which we are dealing right now. Machine learning it's like technologies that can accomplish specific task by learning from data, right? So you give an input and then you have the output, you train the model over that data, and then you try to end up with a model that is learned from your data. And the deep learning it's the subset of machine learning because it's also learning from data, but it's just a specific type of ML using multi-layer neural networks. So since today we are going to talk about neural networks, we will start with explaining how it started. So and then we will try to end up with deep learning. Okay. So what is neural networks? What is deep learning? Neural networks actually it's multi-layer perceptron. So if we have one hidden layer, okay, this is input layer in the neural network, and this is the output layer. So we give some inputs to our networks, and then we have the outputs, and then we try to create a network that could learn from this input by trying to minimize the error. So if we have one layer in the middle, this is called just a neural network. So the deep learning is actually multi-layer perceptron, but when you have more than one hidden layer, it's called deep learning. So this is the only difference actually. So we can say that deep learning is also a neural network, but the multi-layer version of neural network. Okay. So this is the input layer, this is the hidden layer, the red dots, and the output layers are blue. In machine learning, what we do, we give an image or we give some data, and then we have the outputs, right? So as a human, as a data scientist, as a machine learning engineers, we try to build the features so that the model could learn more about my data, and then try to make a reasoning what makes this data point end up with this result, right? So this is machine learning. So as a data scientist, we are usually in the middle, and then try to create some features to help, let's say, classification or regression, and then feed our model into certain machine learning algorithms. It could be deep learning algorithms as well, but the key here is feature extraction. So we do the feature engineering steps in machine learning most of the time by ourselves, or have some tools to do that, of course. In deep learning, we kind of try to give this task like feature extraction or pattern recognition to a deep learning framework, so that we just give the input and then we have the outputs, we build some models, and then try to find a way to represent my data in such a way that it could end up with like predicting the type of the data or the class of the data correctly, right? So that's why deep learning is highly useful if you have like more dimensions like image data, voice data, right? And because you can approximate any function with deep learning, which is called universal approximation theorem. Okay, so basically we try to remove the feature extraction step in deep learning. Like as I said, there are some jokes about this. So is AI just a glorified statistics? Because it has been because it goes back to like 1950s actually. This is not a new, but it wasn't popular that much in the back. Data science or machine learning is the combination of statistics and mathematics and then the business mind actually. So when you just say statistic, it's not popular, it's not very attractive, but in the last few years, people always try to say AI to explain what they are doing, which is wrong actually. So this is whole another topic. There are some papers and articles and the blog posts about this topic. So I'm not going to get into the detail of what is the difference between machine learning or statistic or AI, but I just want to know that it's normal what you see in the media right now. Okay. So why is this popularity? There are some reasons behind this popularity. There are hundreds of papers published every day in machine learning field, and it wasn't that popular before. So there are some reasons that make this field more popular, which I'm going to cover today actually. But I just want you to see that there's an increasing trend towards machine learning and AI architectures, and then business are getting more relying on AI integration every day. Like the research are, no matter which major you are following in universities, people always try to learn machine learning and deep learning to accomplish their tasks. And in every industry right now, try to adopt this technology to increase their sales or profits by paying less, right? So let's start the history, because I'm going to talk about right now why this popularity right now, right? So there are certain reasons for that. The first one is 5 decades of research in machine learning is at the top right now. So this is all started in 1940s. The basic idea was to build some electronic brain by like giving some inputs and then trying to get some outputs that could reason like a human, like XOR gates, right? Or gates and gates. So basic circuits. And then in 1950s, there's a huge invention that is called perceptron. The perceptron is very similar to what we see in neural networks today. You give some continuous inputs and then you try to end up with some discrete outputs with some logic gates. So that was a main milestone. That was one of the major milestones in deep learning research actually. And then the golden age started in deep learning research. So in 1970s, there's some the popularity of AI was very high, and then so much money was flowing towards that research. But then the technology was not enough to accomplish what the researchers have been imagining at that moment. Like everything was on the paper, but the hardware or the capacity of the processors were not enough to accomplish what is claimed on the papers. So dark age, AI winter, you may have been hearing this term a lot. There's a big gap in the history, which is called, like in this domain, of course, which is called AI winter. And it ended with, by the end of 80s, by these popular guys like Hinton, you already know him, I guess, by the invention of backpropagation and multilayer perceptron. Okay, so let's, and then after 2010, with the AlexNet and ImageNet competition, the era that we are in right now has officially started actually. So let's see what was the original idea. The original idea in 1940s, which is called perceptron, and we usually name it with the name of Frank Rosenblatt, actually. So in 1958, Rosenblatt implemented Pitt's neuron, which is claimed in 1940s. So the idea was to use some threshold logic, as you can see here, and then converting the continuous input that is feeding into that threshold into discrete output. So it was basically because people were always writing about artificial intelligence, how brain learns. There are some analogy between the brain and then these systems. So there was some Hebbian learning, which is, in summary, we can say cells that fire together, wire together. So people try to accomplish these ideas on like big machines. The first one was called Mark I perceptron, which is designed by Rosenblatt in 1958, which is the starting of golden age of AI. So it takes one input and some weighted sum, and then returns 0 or 1 given the threshold. This is very similar to what we have been doing so far. So there are some limitations. Of course, there is a big limitation over there. Let's see what happened next. After 1960, people try to focus more on this idea and then try to accomplish something with this perceptrons, but it was very limited because it was hard to train nonlinear. It was hard to represent a nonlinear function with just one single perceptron. And they had an idea of multi-layer perceptron, of course, like using multiple nodes and multiple layers. Right now we have one layer. Actually, we don't have any layer right now in the Mark I perceptron, just one cell, we can call it. And it turned out that the neural networks couldn't be translated effectively into multi-layered neural networks, given the design principles in Mark I perceptron. So, and this book is published by Minsk and Paper, which is called Perceptrons, and there was a huge discussion in the media and then industry. So the money dried up, actually. In 1968, the AI winter started because the capabilities were very limited and it was hard to train any network if you use more than one cell. So AI winter started. In 1965, Hinton published a paper to offer a solution to train large networks like multi-layer perceptrons, which is called backpropagation, and then offer some solution like a gradient descent. I'm sure you already know that. So backpropagation and gradient descent forms the backbone and powerhouse of neural networks at the moment. So it's basically gradient descent constantly updates and moves the weights. The idea was to find a way to update the weights between the neurons, right? So backpropagation and gradient descent allow us to do this and allow us to train multi-layer perceptron. And it was the starting of the new AI era, which is the end of AI winter. So we can say that after 1968, with the invention of backpropagation and gradient descent, the AI winter ended. And it's surprisingly, we are still using these since the last 30 years. So the second reason why this is very popular right now is the increased capacity of the hardware technology and some nice resources from cloud services, like cloud computation sources. So we can call it like people, like researchers, usually use their own machines at that time, and now we are able to use, like, fire up any Colab notebook on our browser and then connect the GPU and then train our models. So there are some processors specifically developed for machine learning and deep learning research, because these are all computationally expensive operations, and GPU and TPU allow us to train large models like 1 billion parameters with the help of giant cloud providers like Google, Amazon, Azure. Okay, this is the second reason why this is popular. The third reason is big data. So right now we have the research is ready, we have the hardware is ready, and the cloud services, big players are in the game. Now, the third reason is lots of data. So due to connected devices and social media and Industry 4.0, so there are many data points. There are billions of data points created every day. And it was hard to utilize these data with the technology that we have been seeing so far. So with the help of deep learning allow us to use more data without losing accuracy. Because other machine learning algorithms that we have been using so far, which are still popular, by the way, that you guys are already learning, may degrade in terms of performance when you feed more data, and it may be hard to train these algorithms under big data. So deep learning is a proven way of getting high accuracy. The more data that you feed, the better accuracy that you get at the end. So this is the third reason. This is just a summary of all the data points that are created every day, which is highly impossible. It would be highly impossible with the technology that are developed like 50 years ago or even the 10 years ago. Right now, that's why there are billions of data points created every day, and people are trying to utilize this data to find a way to implement in their own business so that they could get new insights and predict something that could turn into money, right? The fourth reason would be the ease of implementing these algorithms. Thanks to some researchers and some frameworks like TensorFlow or PyTorch, it's very easy to build such a systems. And it's easy to reproduce some academic papers with the help of these easy-to-use deep learning frameworks. Otherwise, everything that is implemented in deep learning, all these math and ugly computations needs to be done line by line. But these architectures like TensorFlow and PyTorch make it very simple to build any neural network, so that the rest is up to the machine capabilities. Okay. And the last reason is resources and efforts from the large corporations like Google acquired DeepMind, OpenAI or Facebook AI research group. These are all big companies like right now supporting AI research because they are earning a lot. They are spending a lot on R&D, and because they know that in the future or nowadays actually, the leverage that they have right now will not be enough. So they need to invent something. They need to invest more in this kind of research so that they would be leading the industry as they have been doing right now. Okay, so and those are the venues that have the most data actually, like Facebook has all our data and Google as well. So they are just utilizing the data they have with brilliant minds actually. They are finding the best guys out there and then try to invest more to develop new algorithms in this domain. So in AI, there are certain fields that you are already familiar, but people are not aware of some part of AI which is covering. As I said in the first slide, AI is the roof term actually, covering not just ML and DL, but more than that. So we can also call it like expert systems, as you can see in this slide, some automation, some optimization, or like planning process, and robotics. These are all can be named under AI. So the main field of AI right now is like machine learning, which is also covering deep learning. And people usually use that with predictive analytics. So speech to text or text to speech, or computer vision, image recognition, which is very popular, by the way, as you know, and NLP. NLP is like extracting insight from text data, which is highly unstructured and whole and other wild world. Okay. So computer vision, the idea is to be able to detect objects or detect what's in that image, so that the systems would like this kind of operation would be automated, right? So assume that we are working in an autonomous car industry. So the goal was to be able to detect the pedestrian and the cars and the traffic signs, etc. So Anything that can be done by human, it can be done by these kind of architectures. So the goal was to be able to find a model that could understand the image as human can do. So there are many use cases for that, like face recognition or autonomous drive, or some like finding the healthy plant leaves, or finding a tumor in X-ray. These are all the certain use cases of computer vision. The second step is natural language processing, to retrieve information and then use this information to build some like predictive models as a downstream task, right? You can be working on a question answering system and you could have no feature other than text. So natural language processing tries to extract information, hidden information from the text by finding some patterns, and it's also a very vivid research area, by the way, which I'm already working. And there is a combination right now. We cannot think them one by one, because you cannot just say that I'm working in computer vision or NLP. You can work in both, which I'm personally doing. And by using the similar architectures, like computer vision mostly relying on CNN, and NLP is mostly relying on sequential models like RNN. So there are some combinations using CV and NLP in the same application, like the one that you see in the slide right now, like what's going on inside the picture. The search that you are doing on Google right now, kind of using this one, when you write something, when you define something as a string, the images will try to be mapped with this input. So you are not just returned by any, even though without tagging, right? Any picture that you upload to Drive can be extracted, this kind of features from the images, so that it's easy to find. So in sum, AI is everywhere, right? From medicine to education, to space industry, to sport, to autonomous cars, it's everywhere. So we cannot lag behind, and we need to know what's going on here. That's why we are studying this, right? And due to popularity of this field, there are hundreds of, like maybe thousands of companies or startups are flowing into this industry right now, try to implement their work with the help of machine learning and deep learning. Okay, so they call it AI, but they are all trying to leverage the data they have with the help of the recent developments in the machine learning research and the computational resources, etc. Try to make life easier, spend less, earn more with the help of AI. Okay, so let's talk about a little bit of use cases in deep learning. We can the first use case comes into my mind is a face recognition, which is very popular. Even on your phones, there are some face recognition features already implemented. The idea is to be able to find identify a person with the trained models, actually, to be able to find the suspicious people, or for the security systems, or like cardless payments, right? And especially in China, it's like the facial recognition trend is very high, and there are some ethical discussions going on at the moment, actually. So these are all fed by deep learning systems at the moment. The second use case, which I'm personally working at the moment, is medical imaging and diagnostics. There are many new startups aiming to reduce the need to physicians, human physicians, right? Because the number of physicians are fewer, given the number of the patients. And with the help of machine learning and data collected so far, the more sound decisions can be made or automated, and then in short amount of time. Because in medicine, it's easy to beat the human accuracy, in my personal opinion, by the way, because even two doctors do not agree on each other. And the more they learn from each other, the physicians, the better the decisions they have. So it all depending on the use cases they have experienced personally before, which means that they are carrying the information and the knowledge they from their past. So when there are more than one doctors, the decisions are usually better. So that means that if you leverage data in medical domain, you would get some big leaps that you wouldn't get in any other industry. Another hype in this domain is brain-machine interface. In this picture, in this slide, actually, you see some like prosthetics, right? So that could be attached to amputated body parts, right? So the goal is to be able to measure, like they give some signal, right, with some nerves on the arm, for example, and then try to map it with the movement done by the human. Like they say, the patients like squeeze your fist and then raise your finger, etc. And then they measure all these frequencies, all these synapses actually coming from the nerves, and then try to implement the same on some prosthetics and then attach to humans so that it would be able to controlled by human mind. It's kind of sci-fi when you hear like controlling that by human mind, but whenever you see something on the screen, there are some activations happening in your brain. So that's why there are even some researchers to visualize what you are thinking right now. And Neuralink is trying to do a similar thing at the moment. It's another hype in the industry at the moment, actually. Another field is auto claim processing, because right now these kind of industries are manually, like law, medicine, insurance. These industries are relying on human a lot right now. So the more you are relying on human power or the human workforce, the more you have a chance to automate this process and then increase your profit. So that's why auto-claim is one of the popular area at the moment, to be able to find some, like assign some risk score to each drivers, or assessing the claims just by using the computer vision instead of calling some experts, human experts, and then trying to assess something, right? And usually, for example, when you have an accident, the insurance company assigns some experts, and then they try to assign some price and then negotiate with different companies, etc. So it's a long process. In computer vision, you would know, with the help of machine learning, you would know what you will pay in a short amount of time, and then it's all understandable, actually. Another one is anti-counterfeiting. So it's a rare event because these kind of fraud detections are rare in domain. Of course, it's usual, so it's hard to detect. It's kind of anomaly detection problem, which is a very popular and live research area at the moment. This is another nice area that machine learning plays a huge role and then help many financial institutions. Another one is checkout free retail. It's only done by Amazon Go at the moment. The goal was to be able to remove the counters so that people just buy whatever they want, and then they are already checked in with an app when they get into a store. They just, I'm sure that you already have seen some videos and read some papers about this. And then there are thousands of cameras inside the stores, and then you just check out without paying anything, and then you just build. Another hype in the industry is autonomous vehicles. So autonomous vehicles is a long shot, actually, because there are many hard use cases that needs to be get over, but it's still not there yet. We are still not there yet. The goal was to be able to reach level 5 autonomous There are some levels in autonomous car industry actually. So level 5 is even removing the brake pads or driving wheel. So it's not going to happen soon, but many companies are investing right now over that one. So the future is unclear actually, but it's still a very live domain that people are working towards by implementing NLP, computer vision, and even the hardware. And with the help of autonomous vehicles, there will be another issue actually, like the data will quadruple actually, because there will be many data points that will be collected by cars. So it's gonna be another like opportunity actually for us to dive into, to use this data to help the drivers, right? And another area is predictive maintenance. Right now, the maintenance our industry are doing on some regular basis. There are some schedules or the cards that technicians are applying some maintenance after certain amount of time or certain amount of working hours, right? But since the physical characteristic of each device or each machine is different, that breaks up might happen anywhere, and then it costs a lot, like shutdown on during the predictive, like during the plant maintenance. People usually, like companies, usually shut down an entire plant, like a part of a plant actually. So if you're switching from plant maintenance to predictive maintenance, uh, another goal actually right now, and some of the big companies are already implementing, like trying to predict that maintenance before that breakup happens, right? So it's gonna help a lot if this could be accomplished soon. E-commerce is very popular, of course, you already know. So we are usually, especially during this pandemic, people like to shop online. So you don't need to go physically. And then when you shop online, there are many data points that you generate, and all these data points can be used more effectively to sell you even what you don't need actually. So, and then there are some recommendation systems coming towards these e-commerce systems, and it's right now it's the most like in life example of machine learning actually right now. Anything that we do online is used by some companies to sell what they want us to buy, right? And in agriculture, which is less popular but very important for the countries who are relying on agriculture a lot. Netherlands is one of them actually. So instead of doing all this monitoring with human force, the idea was to be able to automate this process and then predict the crop quality or yield amount, right? So that you could know where to like how much you will gather at the end of the year or the season. Okay, so this is another nice implementation area. And Edge AI, which is less popular, just a few guys working in this field. It's like the AI, the machine learning algorithms that are processed locally on a hardware device, like the device that you carry with you. Okay, instead of training these models on large cloud servers dedicated for deep learning architectures, no, the sooner that you have the data on the cell phone, it can be turned into insight with some edge AI algorithms on device. So it's another live area, but it's not popular right now, which because it's also related to algorithms and hardware implementation. So it's a new area at the moment, but it will be very popular soon. And limits and danger of machine learning, let's call it artificial intelligence, because these are all learning systems, right? And you don't know what your model focus more on, like while trying to assign that label to your data. So if you unlock, so in like a attacker can abuse these weaknesses, or these are not weaknesses actually, these are the features that the deep learning models have. So that's why sometimes in deep learning research there are some phenomena that we are not able to explain very well, right? Because it's hard to explain. You would end up with yield sign from stop sign just by adding this perturbation. Okay, or you can change the name of a people by like a through facial recognition. Like you can conceal your identity just by using a glass. Okay, so this is very weird, like hard to understand, but it's happening actually, which is called adversarial machine learning, which is another research area. The basic idea, actually, there are some features in the images that the models are more prone to pay attention. So these are called activations. So if you know, even though these are all black box algorithms, if you give more examples and then check with the outputs, and then you do this enough, you will end up with some pattern, and then you would find some perturbation patterns or some rotation, like a rotation or some noise that you can implement into any image, and then you would ruin the entire prediction actually. And then another handicap, another problematic area in machine learning is that the models, especially deep learning, which they are usually using softmax outputs, right, for the multi-classification problems, they are very confident. The deep learning architects are very confident, even they are not right. As a human, when you see something, like if you are not sure about the type of that image, right, or the answer of the question, you say that, okay, I'm not sure. I'm like 60% or 70% confident that this is right or wrong. But in deep learning architectures, the probability scores, the confidence level is not exactly the way that you are imagining, that you imagine. You will see this when you start working with neural networks, actually. Maybe some of you already work in that field. The output of the like the probability scores coming out of the output layer in neural networks cannot be interpreted as probability level or the confidence level. It's another research area, by the way. So now we are going to jump into neural networks. Let's pause here. Now we are going to learn what's actually happening when we say neural networks or deep learning, how the inner mechanism of the neural networks are. Okay, so as you know, we always use neuron analogy when we try to explain how machine learning, how neural networks learn, right? Because the learning process is quite similar. It's like making an analogy between brain cell, like brain neurons in the brain versus neurons in the neural network. So there are about 100 billion neurons in a human brain. And in physically, actually, this is actually happening when you see on the left-hand side, like this image. Neurons receive electric signals at the dendrites and send them to the axon, right? So, and then each neuron receives input signals from its dendrites and produces an output signal. And then there are some synapses happening between the neurons. It's like, so let's forget about this slide, and I'm gonna tell you something. So, when you start to learn something, at first, when you read something that you don't know very well, you feel nothing, right? When you read, it's very complicated. Assume that you want to learn quantum physics. You have no idea. And then when you read first, you don't understand well. When you read second, you don't understand well. But the more that you read, the better your brain is shaped, right? And then you start to understand, you start to make some reasoning and connect the dots with the previous pages in that book, right? And then you start to understand something, which means that the more that you read, the more that you live through, the more you learn. It's like a toddler, right? Like a baby starts to learn something from its experiences. So, and the more that you focus on one area, the connections in your brain is rewired according to what you read and what you focus more on according to your expertise area. It's like the weights between the axons in your neurons in your brain. So let's get back to the slides again. So this is the neuron that we have in human in neural networks, right? Like we have, this is a cell, like a node. We call it in neural network like a node in any layer, and then there are some inputs like a data points coming to us. So these assume that this is an axon, like in this analogy. So there are some weights, and then it's multiplied by the inputs, and then apply some activation here, and there's some output generated. Let's see how this happens actually in any neural networks right now. So as I mentioned before, there are three components in neural networks, like input layers, output layers, and hidden layers. So layer means the combination of the nodes in the same level, right? And each layer and each node is connected to the next one, like preceding and the following nodes. This is like easy to represent in this way. Of course, it's more complicated than this, but it's very easy to understand when you look at this network like this. Okay, on the right, you see just the weight areas. So each connection between the nodes, okay, are weights, are represented as a weight. So there are some weight assigned to each connection between the neurons. It's like the human neurons connect to each other, but more complex than this one. And there are some data points coming towards to each node, and then all these inputs are multiplied by the weights, and then something happened inside each node, and then generated another output, which is another. There's another weight here. The goal is to be able to find the best weight combination, best connection combination, so that it would represent the inputs, like it would map the input with the output. Okay. So this is our neural network. Each weight is assigned some, each connection between the neurons nodes are assigned some weights. At first we start with randomly, and then they are represented with the starting and ending point of each node on the both end of this line, okay? And then the goal is to find the best weight. So optimization of the neural network, like training the neural network, is all about finding these weights, okay? Because you can you try to find the best optimal weights by giving more data and then seeing what happens at the output, okay? So the network tries to learn which, like the thickness of each connection, let's say, in the human analogy, okay? So even like, and we start with random weights at first, so that and then the model tries to learn. So how it learns? To the input layer, we give assume that this is age, height, weight, okay, like gender, or some images, pixels, okay. So any data point that you have, like the number of hours you study per night versus the grade that you have, right? So these are all data points that you use in any machine learning. Assume that these are all your one single row, okay? One single row of data points. And then you fit this into inputs, like the number of columns is equal to number of nodes in the input layer, okay? So when you fit that data into this input, it at first pass through this way, so you multiply each weight with the data point, and then you sum up. This is a weighted sum, okay? And then you apply activation function. So this three, like sum, activation function, and hidden input is already happening inside here, okay? One single layer. So this is just the explanation what's going on inside. Look, this is one neuron actually. So the neuron takes this input, do some weighted sums, apply activation functions. There are certain activation functions which I'm going to cover today. And then giving some output. Now it's the input to the second layer of nodes, okay? And then this happens again. The more layer you have, this happens more, right? And then you have some outputs. At the end, you compare the output with the ground truth, find the it's called loss, of course, and then you apply back propagation to find to go back and then update all these weight. Weight means all these arrows, okay, between the nodes. Let's do some computation very quick, okay? So assume that this is 2-column data set. It's 6 and 5. So we like 4 rows and 2 columns data set, okay? And we have 2 inputs, 6 and 5, like column 1, column 2, first row. We fit this into this network. The weights are generated. The weighted sum is calculated and activation function is applied in this cell. And then you have the output H1. So H1 is like X1 right here. Okay, now it's the new input. So if there would be another layer, it would be using the like H1 multiplied by W, etc. Okay, so we basically do some matrix multiplication. That's why GPUs or TPUs are very popular right now, because these are all computational expensive operations. It's all mathematics. So instead of trying to do this one by one, like when you try to build this neural network from scratch, you would do many mathematics over there. But right now, it's like using like popular computation libraries like NumPy, even the like a new one. So just the deep learning framework, TensorFlow, PyTorch. You don't need to calculate all this. It's all handled by just writing one single line of code. But under the hood, this is multiplied by this matrix actually, and then this H1, 2, 3 is generated. Okay. So the mathematics part is actually there's also one another parameter here, which is remote for the simplicity. It's called bias. Okay, so you multiply X with W, like the weight, to end up in this cell, but also you need to add some bias for the to represent nonlinearity in your network. Okay, and then you sum up, and then you apply some threshold, and then see. And then find out the output for the next neuron. Okay, so this is what's happening inside one neuron. Okay, there are some mathematical representation that you need to be familiar soon when you start working on this field. But there are most of the time when you are using Keras or PyTorch, you wouldn't need to do any mathematics, but to be able to understand what's going on and interpret your results, you need to see. So the weighted sum is calculated, and then some activation function is applied, and the output is generated. This is the basic steps. Get the input, multiply by weight, add the bias, apply activation, and then create the next input for the next layer. Okay, so let's solve one single problem, very simple problem. Okay, one by one. We have around 20 minutes right now, so I think it's enough. So let's say that this is our 2-column data, the number of hours a student studies, and the number of hours slept, like 2 hours studied and 9 hours slept. And there's an exam tomorrow, and he got 92. So there's another student studied 1 hour and then slept 5 hours, but he got 86. So and then they want us to find out the score of this student who studied 4 hours and slept 8 hours. Okay, so we can, if you have enough data point here, you can approximate this. There's a universal approximation theorem in deep learning research. Okay, with just one single hidden layer, with infinite number of neurons, it basically says, you can approximate any function. You can even fit the randomly guessed numbers. Okay, you can just made up some data points here, like 1,000 of, and then fit it into your network, and then your network would learn it. But of course, it would fail on the real world data because because there's no pattern if it's random. So let's see if there is a pattern between the number of studies and the number of studying hours. Okay. So we take 2 and 9 as an input. So we feed into our input layer as 2 node because it's 2 column. So we randomly generated this weight at first, 0.2, 0.6. Assume that you randomly generated some floats between 0 and 1, okay? 0.2, 0.6, 0.1, 0.8. So you have 1, 2, 3, 4, 6, right? Because you have 2 inputs, and you have in the next layer you have 3 nodes, so you would have 6 connections. Okay, these are all the parameters that the model needs to learn. I'm going to omit bias right now. We usually have bias parameters for each weight, but I'm going to omit this for this calculation. So what we do, let's do some calculation right now. So we have 2 and 9, right? 2 and 9. Now I have as a matrix 0.2, 0.6, 0.1, right? 0.2, 0.6, 0.1, which is coming out of this cell, okay? And the next one is 0.8, 0.3, 0.7 coming out of the second node in my first layer, okay? So I'm going to do matrix multiplication right now, which is basically multiplying like 3 times 0.2 plus 9 times 0.8. Okay, this is like a matrix multiplication in algebra, you remember. And then you create the first parameter here, 7.6. And then you do this for the second. Otherwise, you would do this one by one. But there's a matrix multiplication which makes the life easier for you. And then you will end up with new matrix, which is let's go step by step. Actually, now we have the 7.6 from just first, right? Just by using 2 and 6, like 2 and 6, like 2 and 8 is coming from like 0.2 and 0.6, right? So we do this weighted sum, and then we end up with 7.6. Now 7.6 is written as the first item in my array, and now I do the second calculation. I end up with the, like, when I do this enough for this column, I end up with 3.9, and I do the same for the third column, I end up with 6.5. Okay, so I created the hidden inputs right now. Okay, so these are the inputs for the hidden, because it's multiplied by the weight. So let's do the same. Let's generate some random here. Okay, randoms here. So the goal is to multiply this, like 7.6, 3.9, 6.5. Okay. Actually, not do this. Okay, let's start from scratch, actually. Okay. For this image, so let's solve this problem one by one. As I said, this is the input layer, and we are just taking one row from my data set. The first data point is 6, like 2 and 9, right? So I have the input as a 2 and 9. I have the weights from this connection. Weights are randomly generated as it is, like 2 points, like 0.2, 0.6, 0.1, 0.8, right? Okay, so I have 6 connection because I have 3 nodes in the second layer and 2 nodes in the input layer, so I have 6 connection. So I can just write this as a matrix representation, as you can remember from algebra. Okay, so I will just do some matrix multiplication here. Like the first row of my data set will be multiplied with the weight matrix. When you do this, you end up with this hidden layer inputs. Okay, so this is just for the first hidden layer. Okay, the first node in the first hidden layer, the first row, because you get 2, 9, and then multiply it with 0.2 and 0.8, and then sum up, and you end up with 7.6. And then you do the same for the second column, right? Like 2 multiplied by 0.6 plus 9 multiplied by 0.3, and you end up with 3.9. Okay, so right now we are done with the first calculations, and we have the first row right now. Okay, so this is our first row in our data set. So when we do the same for all the other rows, for all the other inputs, the second set is 1 versus 5. The third set is 3 versus 6, right? I have 3 data points, and it wants me to predict the fourth one, right? So when I do the same with the same weights, because at first when it starts, all these weight connections are random. So I'm going to use the same weights because it's not updated yet. So I will feed all my data once and then update the weights later. Okay, so all the data points needs to pass through all the weights at once. So when you do this, you will end up with this new matrix right now. And now let's see what happens. Right now we did all the math for all the data points. Now we are in the hidden cell. Now we are going to apply activation function on the hidden cell. So as you can see on this slide, we are done with the first row. So the matrix is calculated for all the data points right now. But right now we are going step by step, and for the first data point, I need to apply activation function. So since here right now for the first data point, we are in the hidden layer right now. Now we are going to apply activation, and that 7.6 will become 0.99. Okay, so let's see how we can do this. So when activation function is there are different activation functions in neural networks, but today we are just going to use sigmoid functions. It's just try to squeeze your data points like in numbers between 0 and 1. And this is its representation, mathematical formulation, right? So 7.6, according to this sigmoid function, 7.6, when you go to x-axis, it's around, on the y-axis, it's around 0.99, right? So when you get sigmoid 7.6, you get 99, so 0.99. And you do the same for 3.9, and you get 98. You see? So which means that you are right now squeezing your data between 0 and 1 through the sigmoid function, so that it's kind of normalizing your data, but as well as adding some threshold to your data actually. So for the first data point, now we are done. We end up with these activated functions. These are calculated right now. Okay, so there are different activation functions in deep learning. So we just use the sigmoids. And for example, there are ReLU here. For the ReLU, for example, which is one of the popular one in CNN, actually, CNN architectures, which we usually use after each CNN layer. It's, for example, different than sigmoid. Sigmoid can go from minus, like it also accepts minus inputs, and then activate still pass through. But the ReLU, if it's like a minus, like less than 0, it doesn't fire. That activation doesn't happen, so it just returns 0. So that it's like getting the maximum of the inputs. Okay, so you don't need to know all these right now, but when you start dealing with the deep learning, you will need to learn all this too, because they are all having different attributes given the derivation. Because for the backpropagation, we use derivation, like getting to be able to find the optimal points. Okay, so right now we are done. We get for the first data point. Okay, I'm saying that again. We are still in the first data point. Okay, we usually feed batch by batch. So this learning happens batch by batch for the large data set. But for this simple example, we are doing this one by one, like row by row. So we are still in the first row of our data set. Our first row is fed, and then we got the activated values in the hidden layer. Now we are going to fed into the output layer, because output layer will give me some value, right? The value right now, the ground truth is 92. So let's see what my network learned after first epoch, like first iteration, right? So these are the random weights between the hidden layer and the output layer. Okay, just like the first weights, like in the second layer, there is another random weights that is connecting each node to the output layer. So what I do is I'm just using the values coming from the sigmoid function, and then multiplying and summing up. Okay, weighted sum with the weights, like 0.4, 0.5, 0.9 is coming from these random weights. Okay, so when I do this multiplication and then sum up, I end up with 1.78. So there is another activation function inside this cell. You remember I was showing the inside of each cell. In each cell there is also an activation. So we did activation in hidden. Now we need to do the same here. Okay, This is one of the important field in deep learning. There are some activation functions that can be used in the output layer. For the multi-classification, we use softmax. For the like binary classification, we use sigmoid. Since we are doing regression right now, because we are trying to find this value, we can use just sigmoid. Okay, so we apply sigmoid on this weighted sum. So sigmoid 1.78 is 0.85. So I got a value between 0 and 1 right now. Okay, so now I have this one. So I compare this with my output. So it's there's a, because it couldn't find, so I need to update my weights right now. Okay, the output is 0.85, but the ground truth is 92. So there is a huge difference right now between ground truth and the first output. Okay, so when we do this enough with enough data point and then do the back propagation, these weights will be updated one by one, so that it will like whenever you fit this one, you will end up with 92, 91, something like this, like after 100 iteration, for example. Okay, so you just show the model, present some samples again and again. You say that, okay, I fit this one, I end up with this one, and then it's like teaching a kid. Okay, that kid knows what to say next. Okay, it's like learning any language. So at the last step, when we get the final output, we compare with the ground truth. Now we apply backpropagation. Backpropagation is the reason that this AI summer started, as I explained before. Right, backpropagation is the way of letting us training multi-layer perceptrons and then the gradient descent. So it just finds the difference in the desired values, like a loss, and then goes back and then update all the weights through derivation and chain matrix rules. Okay, so I'm not going to cover this here. Backpropagation is a long subject, but you will, if you get that course, like deep learning course, next semester or next year, you will be able to learn all this. Okay, so we basically have the inputs, random outputs, we get the weighted sums. Okay, applied activation, and then the output of the activation is applied another weighted sum with the next weights, and then summed up, and then applied activation, and now we have the output. So this is what happens when you dot fit in neural networks. Okay, and you need to know that there are still many topics in deep learning that's still not clear for the researchers. We sometimes observe some behaviors from the network, and then we fail to understand fully. This is a simple network, it's easy to understand, because as a human mind I can follow, right? But if this is like 100 different nodes here happening, and there are thousands of layers, maybe, it's weird by the way, or thousands of nodes in each layer, so it would be hard to go back and follow the back propagation one by one on the paper. It would be very hard. So you may not be able to understand, we may not be able to understand actually some of the reasons. That's why they call it black box. Okay, this is simple, easy to understand, but there are the networks that we are using in the real world are highly complex, and that's why people usually complain about being black box. And there are another research going on right now, explainable AI called it. Okay, so at the end we have the loss functions. Loss functions are try to minimize the loss, like between the difference between the output, like predicted output versus ground truth. So we found 0.85, right? The ground truth was 95. So we get when you get the difference, there's a big scalar value over there. So now if you feed all your data point, you will end up with some mean absolute error, right? There are some different loss functions. That's why sometimes mean squared error loss, sometimes mean absolute error. So it depends on the problem that you are working on. If you are doing binary classification, we were doing regression, right, in this presentation. So it should be it might be some of the one of these three functions you can select. And when you select this one, you do during backpropagation and gradient descent, you try to minimize this loss. So if you have a regression problem, so final activation layer should be linear activation and then loss function. These are all the suggested activation functions and loss functions given the problems that you have. So these are not like written on the stone. Of course, you can play with different parameters, but these are some of the starting points that you may want to start. You don't need to memorize because you will feel when you start working on this, okay? And another important concept in deep learning is optimization functions. We said that during backpropagation and using the loss function, we try to minimize the loss, right? So how do we optimize a function that is a combination of billions of parameters? We are talking about like billions and millions of parameters, by the way, because every node, every edge, every bias, every activation, these are all parameters. So that needs to be tuned, like tuning the knob to be able to find the perfect balance in the network. So to be able to optimize millions of parameters at the same time, there are certain optimization functions, but we usually there are some suggested ones like stochastic gradient descent, momentum, adaptive gradient descent, etc. Okay, just like activation functions, we have 7 to 8 different optimization functions that we usually use. You don't need to, for the starter, you don't need to know all of these. You can just like stick to Adam or SGD for the beginning, and then it will be trying to find the optimal point in your network. In deep learning, the problem is convex, which means that there might be like a non-convex problem, so there might be multiple solutions. So there might be some local minimas and the global minimas. So that's why we end up with different results given different optimization functions or iteration numbers that we use. That's why we are using hyperparameter tuning in every machine learning algorithm. Just like you tune random forest algorithm with different parameters, in deep learning, the number of parameters that you need to play with is more than that. So that's why the optimization functions are really important concept in deep learning. Okay, so let's do something in sklearn, because you guys are using sklearn for like machine learning problems, I guess. So this classification problem, this regression problem that we just solved, like the number of hours studied and number of hours slept, and predicting the score, like an exam score, right? So let's do this with multi-layer perceptron in sklearn. In sklearn, there's a multi-layer perceptron module, just like any other regressor. You will just import it from neural network, import MLP regressor. Okay, so you apply all the things as you have been doing with like splitting your data set. It's same as that you do with other algorithms that you use in machine learning. And then we need to scale, right? We need to scale our inputs. Why is that important? As we can go back, like why is that scaling is important? If we end up with like a huge value, because these values will change, right? Right now it's between 0 and 1, okay? But there's a big difference between the like a big gap between the output and desired output and the predicted output. So these weights will change to be able to end up with this score, which means that there will be some weights will have very low scores, like very low weights. Some edges will have large ones. So which means that the model, if you don't scale, it's very important, by the way, you need to scale. But in the deep learning frameworks like TensorFlow, like PyTorch, etc., you for the image classification problem, especially, you don't even need to worry about. You just scale once your image, and then that's all. Anyway, so we scale and then we fit. It's like any other machine learning algorithm, right? So before fitting, let's define our architecture. In our architecture, we say that because the MLP regressor already knows the number of input nodes, because its number of columns is equal to number of input nodes, right? We have 2 columns, which means we have 2 input layers. So in deep learning architectures, we usually do not define the number of input shapes. Okay. In Keras, we do this because of the image recognition problems, but in here, in MLP, the things that you write here is the number of nodes in the second layer. If you add one more, like if you want to use 3 hidden layers, you can say like 3 nodes in the first hidden layer, 6 nodes in the second hidden layer, 1 node in the third hidden layer. Okay, the output layer will always be, since this is a regressor, will always be 1. Okay, 1 node. So we say that use sigmoid function to activate on each node, and then iterate this 1000 times. Okay, and then these are my scale data, and then the target value. So this is simple neural network. When you add 2 more hidden layers, you end up with deep neural networks. So deep learning, this is what they call it, deep learning. Okay. So I defined 3 hidden layers here. So let's do the same with Keras and then explain the number of parameters, how number of parameters are calculated. Okay, so in Keras, this is actually, Keras is right now the part of TensorFlow, so you can also use it as a part of like tf.keras, but you can still use old version of Keras and then import just Keras itself. Okay, you do this exactly the same as sklearn, but here you define your network. Keras or PyTorch will give you more flexibility in defining your network. There are multiple APIs to do this. Let's use sequential API. We will say that, okay, I'm going to build a sequential neural network, like a feed-forward network, because there are different ones, but we'll just focus on sequential ones. And I'll say that, okay, I already, the first hidden layer should have 3 nodes. Dense means that like every node is connected to each other, which is called dense in Keras language. Okay, the activation should be sigmoid at each node, and the input shape of this network, like this dense layer, will be the shape of the input features, right? So it will be 2, right? So I have 2 columns, so its shape is like the second dimension of that shape is 2. Right? So, and then that's all. I don't need to add any other layer because I want to add 1 layer. Then I compile. While I'm compiling, I'm selecting the optimization function as well, which I'm not able to do this in sklearn. There are some ways to do this, but for the beginners, it might be tricky. So, but in Keras, you can just say optimizer is Adam within the quotation mark, by the way. And then loss function should be mean squared error. And then give me the metrics, because during the iteration you may want to monitor your loss function, like loss results, like loss, validation loss, training loss, etc. And then fit 100 EPO, and then use 5% of entire data set as a validation split, so that after each EPO you would be able to get validation metrics as well, so that you can monitor your model, right? If you monitor your trainings, like we call it babysitting your model, you will be able to see when to stop. There are some, by the way, concepts like early stopping that you can set if there is no improvement for 20 iterations, stop, etc. But for the beginning, if you monitor your trainings, if your training loss starts to improve, but validation is getting worse, which means that the model is overfitting, so you need to stop, etc. Okay, this is important to this is very important, setting the validation speed. If you want to do the deep neural network in Keras, you will do the second line again and again with the number of nodes required. Okay, and right now you are able to define which activation should be used in which layer. So I say that, okay, in the first hidden layer use ReLU activation. In the second, use ReLU again. In the third hidden layer, use linear activation. And then compile, which means that, okay, I'm done. So let's see how many parameters do I have. How do we calculate this? Because whenever you write compile, and then print model.summary, you will end up with these tables, okay? So for the first case, it says 9 parameters. Why do we have 9 parameters? Let's go back and then see. If I have 1, okay, I'm going back right now. I have 1 layer. Why do I have 9 parameters right now? You see, I have 6 here. I have 3 here. which means that I have right now 9 parameters, right? 9 parameters to tune, to update each time. Okay. So I'm here. So when I for this one, you also count like the weights and also the biases as well at first. I'm omitting the bias at the moment right now. So like the first one, it's 9, the same as. Since I have another layer which is 6 nodes, so it will be 6 times 3, which is 24, right? And then so on. Okay. Now we learned how to do this. So fully connected networks. Now we are done with the calculations. We can talk about the fully connected networks and different versions of, by the way, different versions of deep learning architecture. So fully connected means that every node is connected to every other nodes in the same network in the next layer. Okay, this is called fully connected FC networks. CNNs are very useful and for image recognition purposes, because in images you have like the number of features you have are a lot. For example, assume that this is 256 times 256 pixel, because this image will be represented as a number, right? So there will be like 0101. So there are more than 1 million dimension. So which means that you would need million input nodes, which is infeasible for the model. It's feasible, it can train, but you can just add one hidden layer maybe. And then if you use fully connected right now, for example, here, there will be millions of nodes here, and then another millions of, and then if you use more than this, your memory will blow up, right? So you will not be able to train this, or this will be very slow. In CNN, there's a nice architecture, there's a nice research over there. So it's like learning as human learns, like creating some features one by one. Like at first learning the edges, and then the colors, and then the vertical lines, etc. That way, there are some concepts in CNN like pooling, batch normalization, etc. So that the model is at each iteration learns different feature of the image, so it doesn't need to see the entire landscape of an image for the input. And then at the end, you feed the output of the last CNN layer to a fully connected network, and then you get the output. Okay. So there are the number of trainable parameters in CNN is less than the number of parameters if you would do the same in fully connected networks. That's why it's faster and it's more useful in CNN in image recognition, computer vision problems. Okay. The other one is RNN. RNN means recurrent neural network. It's basically used in NLP problems, like natural language processing task. And then since it's a sequential, the model, the network needs to memorize the previous steps. That's why we call it like long short-term memory. STM means long short-term memory. There are some connections, like not just feeding the next one, also having a connection to insight, so that it would there are some, like the input of the cells are different than what you have seen so far. By the way, there are some forget gate, remember gate, etc. inside the cells, so that it would be able to remember the previous steps given the window size that you give. Okay. Autoencoder networks is just trying to represent the same given the input. So you give a dog image and then you try to end up with the dog image. So you have an compressed, you have an like a zipping operation here. So when you train this further, this architecture, this small part, like autoencoder part, is able to compress the image, like represent the same image by squeezing some features, so that it's like a dimension reduction in neural network. So it's highly useful to find anomalies or imbalanced data set. It's very useful architecture, autoencoders. And generative adversarial networks, you are following this from media and social media. It's very popular at the moment. According to some research, it's one of the most exciting research area in the last 5 years of machine learning. So it's just training two different networks like generator and discriminator so that it would be able to tune both network to be able to generate the same image or same data point, which means that this could be used generate new data set given your distribution. It's just trying to mimic the distribution of your data set. Okay, it can be used to create new images. It can be create like augmenting your data set, etc. And the last one is pre-trained CNN architectures. Since 2010, right, like ImageNet competition and the starting of AlexNet changed everything in deep learning field. Since then, there are many different architectures are developed like Inception, ResNet, VGG. These are all different state-of-the-art architectures that are doing well or worse given the comparison on ImageNet datasets or some other image benchmark datasets. So what we usually do is these frameworks are usually trained and the weights are saved, which means that these networks, when you save the weights after training, like saving the parameters, like saving the checkpoints, let's say, you can just use these checkpoints on any other image test. So you can use this like VGG16 pre-trained checkpoints, cut the head, we call this cutting the head classifier head, and then connect another fully connected layers at the end, and then unfreeze the previous layer and feed your 100 image, for example. So you don't need to train again and again because it will start from some nice checkpoints, nice weights. Otherwise, you would need to train this again and again, and it would be very expensive. So in image recognition problems right now, this is a de facto solution. We usually start with pre-trained weights. Okay. So I'm done. I hope you like it. Actually, this is a very exciting and very long debates going on at the moment. And as a researchers, we are still not fully aware of the future of this field, but it's very exciting. Every day there are hundreds of papers are being published, and it's a very exciting age to live in right now. Please, I hope you like it. You can get in touch with me if you need further suggestions or resources. I would be happy to help. Hope to see you in campus when this pandemic is over. Thank you.